You know, we hear all the time about making AI models bigger and bigger. But what if the real secret to making them smarter is actually making their training process, well, calmer? Today, we're going to break down this really fascinating paper that lays out a kind of secret recipe for stable AI training, and it might just unlock a whole new level of performance. So, where's this all coming from? It's a paper from the QN team over at Alibaba called Stabilizing Reinforcement Learning with LLMs. And what they're doing is tackling one of the biggest, most frustrating challenges in AI today. How do you teach a model really complex reasoning in a way that's stable and predictable, instead of, chaotic and totally unreliable? And this question gets right to the heart of the problem. Think about it. Language models build their answers token by token, basically one word at a time. But we can only tell them, hey, good job, after they've finished the entire response. This creates this fundamental mismatch that researchers have been banging their heads against for years. Okay, so this mismatch, it leads to a really shaky foundation for training. The paper talks about it in terms of two different kinds of drift. These are the two culprits that can secretly, quietly, sabotage an AI's entire learning process. So let's meet them.
First up, we've got the training inference discrepancy. Here's an analogy. Imagine you practice for a marathon entirely on a nice, smooth, predictable treadmill. But then the actual race, it's on hilly, unpredictable asphalt, right? The two environments are just slightly different, but those tiny differences can completely throw off your performance. It's the same with AI. The engine that generates the text is just a little different from the engine that updates the model, and that causes it to learn from a slightly distorted version of its own actions.
And then there's the second villain, policy staleness. This is kind of like a football coach who's reviewing game tape and giving you feedback on a play, but your team has already run 3 more plays since then. The feedback is based on outdated information. To be efficient, AI training often uses old data to update a newer version of the model, and that creates a stale learning signal. And this right here just lays out the conflict perfectly. Our goal is at the sequence level. We want a great final answer, but the method we use is at the token level, just smearing that final reward across every single word that got us there. I mean, it feels like a clumsy hack, right? A shortcut that really shouldn't work. But here's the twist. This is the big aha moment of the paper. It turns out this method isn't fundamentally wrong at all. It's just been misunderstood. So let's see how these researchers totally reframe this problem and give us a new way to think about it. And this is the question on every researcher's mind, right? With all these drift issues and these weird mismatches, are we building our most advanced AI on a foundation of sand? And the answer, according to this paper, is a big, resounding no. The shortcut actually works. In fact, it's mathematically sound. But, and this is a huge but, there's a catch. It's only valid if those two drifts we just talked about are kept on a very, very short leash. Okay, this slide gets to the core theoretical insight. The paper argues that our token-level shortcut is actually a valid first-order approximation of the real sequence-level goal. So in simple terms, it's a reliable mathematical estimate. But like any estimate, it's only accurate under the right conditions. If those two drifts get too big, the estimate becomes garbage. The approximation breaks down, and your training completely collapses. And just when we think we have a handle on it, of course, things get more complicated. We need to talk about a specific, very powerful type of AI architecture, mixture of experts models, or MOEs. See, MOE models are designed for efficiency. Instead of using the entire gigantic network for every single calculation, they dynamically route data to little specialized expert subnetworks. The problem? Well, this dynamic routing makes both of our drift villains even worse. The path the data takes can change unpredictably between when the text is generated and when the model learns, which just amplifies that discrepancy and staleness. So we have the theory, we have the complications. Now, let's get to the good part. Let's talk about the practical recipe these researchers developed to solve these problems and finally achieve stable training. And the recipe has 3 key ingredients. First, importance sampling. That's a math technique to correct for that treadmill versus asphalt problem. Second is clipping, which basically puts a speed limit on the model's updates to control that policy staleness. And third, for those super complex MOE models, they have this really clever trick called routing replay. Routing replay is it's so clever. When the model is learning from what it did in the past, you literally force it to send the data down the exact same expert pathways it used the first time around. This totally eliminates the drift caused by changing routes.
It makes the complex MOE model behave like a simple, dense model during the update, which is much, much easier to stabilize. Okay, so theory is one thing, but does this recipe actually work in the real world? Well, the paper provides some pretty dramatic experimental evidence. We're talking about a 30 billion parameter model run for hundreds of thousands of GPU hours just to prove their point. So let's look at the data. In a simple setup, the blue bar on the left shows the model with important sampling learns nice and steady. But now look what happens without it. The model's performance doesn't just stall out, it completely collapses. This proves that correcting for that training inference drift is absolutely 100% non-negotiable. Now, let's crank up the difficulty. We move to off-policy training, which is more efficient but makes policy stillness a much bigger problem. And look, the bar on the left with both routing replay and clipping shows stable training and performance just climbs. But take away that clipping ingredient, and you see the exact same story. Performance hits a wall and just collapses. And this quote from the paper just sums it all up perfectly. As soon as you start pushing for more efficiency, you absolutely need these stabilization techniques. They're not just helpful, they are essential. They're the only thing preventing total failure. But this, for my money, is the most powerful result in the whole paper. The researchers started with 3 different models, each one fine-tuned on data from a different frontier model. Now, you would expect them to perform differently, right? But when they were trained with this stable recipe, look at that. They all converged to the exact same high level of performance. So the big takeaway here is this. The process matters way more than the starting line. It suggests that if you have a stable, reliable reinforcement learning process, you can consistently level up a model's abilities no matter where it started. It shifts the whole game from hunting for some magical data to engineering a robust, repeatable learning process. And that leaves us with this really fascinating final thought. For years, the instability of this kind of training has been a huge barrier, a roadblock. But if that barrier is now being replaced by a clear, repeatable recipe, it frees up researchers to push AI into way more complex problem-solving domains. So the question isn't just if we can scale these models anymore. The real question is, what are we going to teach them to do now that we finally can?